Okay, so quickly I'm going to go through the first couple, and then the last one I'll do dimensional analysis for you, okay? So the first one, how many sig figs are in this measurement? You said decimal is what? Present, so you start from the Pacific, and once you start counting, you don't stop. Most of us got this right. This is the little quiz that's in front of you. Everybody have it? Yeah? Maddie? Yeah? Okay. So you start counting, you see 5 sig figs. Don't stop counting. Rounding these. Now, I think at this point we've had like a couple more days of practice with this, but you need to work on rounding where you don't actually change the number, like the size of the number. So if it's really a really small number, you need to keep it really small. You're just gonna adjust the last digit or the last couple digits to either put zeros all the way or around that previous number. You're not actually like literally changing the true quantity of it too much. Very little, okay? So if you want 2 sig figs here, you look and you look, you notice that these first 2 zeros, are they significant? No. Okay, so you have to have them there because they're placeholders. And the only reason you have a placeholder is because it's like, this is a really tiny number. You need to keep that 0 there so you don't round it in a way that makes it a bit much bigger number. So the 0 and the 0 have to stay. These are going to be the 2 significant numbers you need to keep, the 8 and the 2, right? But always look at the next number and say, is that 2 influenced by the 8? Yeah, so you always want to round it appropriately up to the 3 number here. So 0.83, see it's really similar to the pad, we just rounded the last digit. This one right here was a little harder because you had to round this one to 20, so you said the 19 is going to stay with us for 2 sig figs, but then that 7 influences the 9 to go up. Most of us wrote this. How many sig figs are there? 1, okay? So to make this look like 2 sig figs, you can either put a decimal there to say this 0 is significant, put a decimal after it. It's still 20, that decimal means something to us now. Or you can say 2.0 times 10 to the 1st degree C. That'll just look funky, but it still works. It's just showing you know how to do sig figs. Last one that everybody got, 6 to 9 stay, 0 doesn't influence it, so it's 6,900. I think everybody was good there. Okay, and I think most people were good number 3. How are you going to tell something is precise? What are you going to notice about the numbers? Really close together. It's clumped. Okay, even if it's not right, and you know you're hitting the upper left part of or upper right part of a bullseye, you're not on the bullseye. So the ones that are close together are this one. So this one would be precise. And then if the true measure is 2.56, these numbers, they're not incredibly close to 2.56, but they're closer than these are. These are like 0.2-ish off. These are the 0.6 and 0.6, so they're closer to that overall. So this would be more accurate. Okay. This was the one that we just need to practice with the percent error. And I think after your lab yesterday, you're pretty confident in that one now. So if you have a student that's measuring, the student is experimentally measuring 4.8 grams per centimeter cubed, and the accepted value, this is the true value, in a reliable handbook, that's usually where we get stuff, or online, is that value. How do you find percent error? What's the formula? Okay, I'll go experimental minus accepted, absolute value, right? Right, divided by accepted. So, and I don't care if you put E minus A or A minus E, it doesn't matter because it's absolute value. And then, yeah, don't forget to multiply by 100, which some of us got that first part and then forgot to multiply by 100. So, whenever you're doing this for sig figs, this is the only part that people kind of had a little oopsie moment here. So, I'm going to write this down here. 4.80 grams per centimeter cubed minus 5.10 grams per centimeter cubed over, what's the accepted value? Thank you, 5.1 grams per centimeter cubed times 100. So when you do this, what is 4.8 minus 5.1? Or what's the difference? 0.3, right? So 0.3. But ignoring the fact that you have a fraction here, how many when you're subtracting numbers, how do you control the sig fig or decimal? What's important here? Decimal places, right? How many decimal places? 2 and 2. So when you record that, you're going to write that as 0.30 because you need 2 decimals as stated from your subtraction here. Okay? That's just going to influence your final sig fig number, and that's just, you have to be aware of that most of the time. So then we're going to divide by the 5.1, that was grams per centimeter cubed. Grams per centimeter cubed, well, they both cancel, right? And times 100. So then it was 0.30 divided by 5.10. Well, who's the limiting factor here? How many sig figs in the final answer? 2. That one has 2 sig figs, okay? And that was 5.9, because it was 5.88, but because you had to limit it to 2 sig figs only, it was 5.9. So that was a little picky and more 2 or 3 step process, but that's, I only took off half. I usually take off half points for sig figs not being right, or if you don't write a unit or something, so I try to give you most of your credit there. Okay, last one, dimensional analysis, here we go. What is your given data point in this problem? Thank you, 2.322 liters of this acid. And then you've got a conversion factor. Anytime you have a fractional unit, that is a conversion factor. Do not start with your conversion factor. Conversion factors help you convert from something to something else. So you have to start with something first. That something is the 2.322. So it says 2.322 liters, and then you want to use that. But notice there's no liters in there. What is your very first step? Liters to milliliters, because you have to get to a usable unit so you can actually use your conversion factor. So we're going to use 1 liter is 1,000 or 10 to the third milliliters, allowing us to cancel liters out. And then your final step, you can actually implement that conversion factor given to you, which was 1.19 grams per 1 milliliter, because there's a 1 right there. So I know I have to, like in the problems, I have to put a slash there. I can't make it always a fraction like that. You guys, sometimes we're putting that whole shebang on top. You want to separate it so you can cancel your units. So milliliters and milliliters, that was like 2,763 grams. Is that what you guys got? 2,763? What's wrong with that though? Sig figs, right. So you see your first piece of information has 4 sig figs. This is a metric conversion here, ignoring sig figs, remember, just anything with like just milliliters to kiloliters, something with your little King Henry Dye drinking chocolate milk, that metric system there. But then this is density. Density is something that's a significant measurement, right? So there's only 3 sig figs here, so this needs to be rounded to what? 3 sig figs, so 2,760. That 3 does not influence the 6 to go up, so it's just a 0 placeholder to say it's still a 2,000 number grams. Cool? You guys feel a little bit better about some of that stuff now? I think after a couple days it sinks in too. So, okay, let's do 15 or so minutes of practice. On here, this is what I was going to do yesterday, we didn't get to it. We're going to do the first 15 today, and we'll do the last 14 on Monday. This is really, really good multiple choice practice for the test, okay? And the test is on Tuesday, so I try to give you some guided practice here first, because you'll notice this does not sound like me. This sounds like a textbook. Okay? I can only make up so many chemistry problems before I start losing my mind, okay? So I have to pull certain things from the textbook, so that's why I have this here for you. I'm going to do the first 1 or 2 with you because they're heavy on that math and dimensional analysis, and I'll let you guys do the rest and we'll check them. Okay, so let's do the 1 and 2 together. Number 1's gonna blow your mind with me right here. It's a little dimensional analysis. Ready, buddies? Okay, so as we go, I'm just going to kind of write down the information that I actually need, because I don't want to reread this problem 15 times. It is estimated that uranium is relatively common in the Earth's crust, occurring in amounts of, here's my first conversion factor, 4 grams of uranium, because that's what it's talking about, in 1 metric ton. You're like, okay, so it's looking kind of crazy so far. Then it says a metric ton is 1,000 kilograms, right? So I can right now look right here, and can I replace this with a number? I can, right? Because it says it's 1,000 kilograms. I'm going to go ahead and go straight to that, because metric ton to me means absolutely nothing. I don't even know what a ton is, right? So I'm going to erase that, and it just told me 1 metric ton was 1,000 kilograms. All right, so I just adjusted that conversion factor because I read the second sentence. All right. But it says, I'm going to reread it. It says, relatively uncommon in the Earth's crust, occurring in amounts of 4 grams per metric ton. Metric ton of what? What's it talking about there? Uranium or the crust? Come on, guys. The crust, right? Because it's saying it's relatively common in the Earth's crust. So uranium in the crust. So this is uranium in the crust. Okay. At this concentration, what mass of uranium? So question, mass, which is grams, of uranium is present in 1.0 milligrams of the Earth's crust. So this one's really complex. Okay, just you have to deal with me here, but it's really good practice because if you can get this, test will be super duper easy for you. Okay, so I have to label who is who because I'm seeing that I'm really dealing with two different things: uranium and the crust. Of these three things, I don't even have to read the problem anymore. Which do I start with? What do you say? Right, 1.0 milligrams of crust. This is a question. This is a starting point. This is a conversion factor. And then, of course, in the back of my mind, I've got all those metric conversion factors that I can also use because I definitely will have to here. So 1 milligram of crust. I can't do crap with milligrams. What do you guys want me to do? Thoughts? Okay, you want to go straight to kilograms? I'm good with that. Why are you going straight to kilograms? Yes. You see, that's the only thing you have to deal with, right? So you've got to get to kilograms before you can even use that conversion factor. So in your mind, you're going, King Henry died by drinking chocolate milk, ... micro, ... nano, ... pico. Okay, so milligrams to kilograms. Millis are here, right? I don't want to put a 1 there, actually. So millis are there. Who's bigger? I'm going to put milli down here and kilogram up here. Who's bigger? Kilograms. So how many little millis are in a kilo? 10 to the 6th, right? So 1 huge kilogram has 1,000,000, or 10 to the 6th, milligrams. Okay, my life's getting easier here. So this was kilograms of crust. I'm writing this here for us here, so we don't mix ourselves up. So milligrams of crust and milligrams of crust are gone. Now I'm to the point where I can use a conversion factor, right? Because I see kilograms of crust right here, and I can implement it as the ratio is written. So I'm going to put that thing here, 1,000 kilograms of crust, and on top, 4 grams of uranium. Okay, to my desired unit? Yeah, cool. So I'm out here, okay? So my kilograms of crust go away. So 1 divided by 10 to the 6 times 4 over 1,000. Try that in your calculator. Make sure that you're good with your parentheses or whatever you need to do. If you have it in your phone, you can try it on your phone, but you know you have to have a calculator on test day. There's no phones on test day. So 1 divided by 10 to the 6. And then you can either say equals, and then times 4 equals, divide by 1,000 equals, or you can put it as a parentheses, because your calculator don't know what you want unless you tell it. When you get it, tell me in scientific notation. Go for it, Aaron.
4 times 3
to the negative 8.
6,
I got to the negative 9. To the negative 9? I think maybe you just missed a 0. Is it? Maybe you just forgot 1,000 over there? Maybe.
Oh, yeah, I can find it by
there you go. So you can go back and look. So I got 4 times 10 to the negative 9. What are the units here, though? Units?
Oh,
Mm-mm. Grams of uranium, right? Okay. Do you see that answer on there? No? Okay. So that means you've got to just look at this and adjust it to one of the answer choices. When you're looking at the answer choices, you got nanograms, micrograms, milligrams, grams, and centigrams. So we all know it's not D, because D is in grams, and this is the answer. It's 10 to the negative 9th grams, not 10 to the negative 5th grams. So what does 9 remind you of on the number line? Which one? Nano, right, nano 9. Because if you go over 3 more, not from kilo though, if you go over from the base unit here, base, which is grams, has 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 zeros means 10 to the ninth. So 1 gram has 10 to the ninth nanograms. In your head, you're going, okay, 1 gram is equal to 10 to the ninth nanograms. Can you use that conversion factor here? Shake your head, people. You can. Okay. This is in grams. That's a gram, right? So 1 gram is equal to 10 to the ninth nanograms. Let's see if this works. Well, anything that's got 10 to the negative ninth times 10 to the positive ninth, they kind of cancel each other out, right? You could actually plug in your calculator to prove it to yourself, too. So these two things are going to cancel each other out, and you're stuck with 4. Answer. 4 grams of uranium cancels with grams of uranium. 4 nanograms is the answer. And I think we're going to correct sig figs because 4 was to 1 sig fig here, so that was our limiting factor. Okay, that is the absolute hardest potential analysis you would even not see. Okay, you're not going to see something extremely that hard, but if you can get that, you can get any dimensional analysis. Okay, questions on that one? Okay, how about I'm going to let you guys don't do 2, go ahead and do 3 through 9 for me, then we'll check those, okay? 3 through 9. You guys can work with a partner on that. And then we'll go to the lab and we'll finish this when we come back if we need to. Talk to a buddy on it. No, don't do 2 right now. We'll do that one later. You guys are doing 3 through 9. I have periodic table notes, but I think a lot of the stuff you saw in your video. So I'm going to ask for you to be responsible. And if you need some more help with this, if you're unfamiliar with this from the video, then you're going to go back and take some notes, but not right now. Okay? Because it's pretty much talking really similarly what you went through. And, oh, sorry, let me show you this. I do have if you have a QR code reader, you can download one. But I do have it here, and you can pull it up on your phone when you're in the lab waiting on your results from the chromatography experiment. So I have that here, and I'll have it on my board as well. So if you don't know how to use a QR code reader, I'll show you. So you'll see some of these things, Mendeleev, that are fairly familiar to you. Metals, and non-metals, their characteristics. Those are things you might be already familiar with. The only thing I can't remember if it's on videos, groups are what go down the periodic table, the columns, and periods are across, they're the rows. So that's just a distinguishing vocabulary term we use for columns versus rows, or groups versus periods. You can see that here as well. So it's very simplistic baby information on the periodic table so far, but I do have names of these different groups, and you'll probably saw some of that on your video, but you'll be using that information on the worksheet as you guys are waiting your lab results. And these are characteristics of each group. So this looks like a lot of information, but metallic, non-metallic, metalloids, non-metalloids. So they're just very kind of baby information on each of these. So on the lab, I have done a lot for you. I've already cut your strips into equal pieces for you, but what you're doing is you have chromatography strips. You're separating mixtures. The mixtures are dyes. The dyes are Sharpies, okay? Sharpies are made of multiple mixtures of things, okay? But if in your lab group, you only get 1 Sharpie, because I want you to have a controlled experiment. You're going to have 1 Sharpie, and you're using different solvents on that single colored Sharpie to see which separates it the best. So your group might use a black Sharpie, your group might use a red Sharpie, your group might use a purple Sharpie. We can see all of each other's results at the end, but you can't mix Sharpies, then you're changing 2 variables, and it's not a controlled experiment anymore, and you can't determine crap. Okay? So I've already done the cutting of the strips for you. You do have to cut a little V shape in your strips, though, and then on there you're going to use a ruler, and you're going to draw in pencil, not pen, because pen has dyes in it, right, and inks, and it's going to mess up your results. Make a line, straight line, and that's going to be your origin. That's where you're going to put the dot of Sharpie. And it's going to run up to about a centimeter from the top of your strip. That's the finish line. So it's slowly over time going to travel up until it reaches the finish line. Once it gets there, though, you got to take it off of out of the solvents, and you got to look at the results and measure the results. So make sure you draw your finish line and origin line after you cut it into a little V, and you cannot let this dot, where your dye is, touch the solvent. You're going to have about 3 milliliters of solvent in the bottom of a beaker. You're going to put your little piece of paper in there. The bottom of the V can touch the liquid, but the dot cannot, because if it does, it's going to go down in here, and you're going to have like purple water and no results. Okay, because it's going to be very soluble in the solvent, but we want the solvent to carry it up as it evaporates up the strip. Let's see here. Anything else I need to tell you? Yeah, we'll get everybody's information from their dyes up here. So after you make your strips and you get your data, if you had an ethanol one, just put it in the ethanol column, isopropyl alcohol column, and water column. So in the lab, it calls for 2 beakers. I want you to use 3 beakers. 1 beaker for water, 1 for ethanol, and 1 for isopropyl alcohol, because you were comparing all 3 of these solvents on its ability to separate the mixture of dyes. Okay, so in the lab it calls for 3, and for 2 I want 3 though. So here's basically what you're setting up. Right here. Water, ethanol, isopropyl, ... liquid, liquid, liquid. And I put popsicle sticks back there to help you kind of tape the paper to it so it doesn't fall
Please
down.
provide interruption.
You can also
Please put
take
your
it.
recycle bins outside of your doors. Thank you.
You can also tape your strip to like the little metallic columns that are, those poles that are sitting up on your lab stations, okay? Pretty much the strips don't want to be laying in the water, they just want to kind of touch the water. Alright, so I think you guys are good. Everything's at your lab station. You will need goggles, but you can take goggle breaks as you need to. Not yet, because I want you to use them for, I'll tell you. Because look right here, while we wait, begin the periodic table sheet, you might need your information. Whenever we get set up, I'll kind of collect your thoughts again. Hey, you're going to use your glasses. So special. Where are my glasses? They're in my chem club.
I'll look them over.
So you guys can kind of get some stuff set up and I'll put it back together. Let me tell you, I see a lot of people sitting because they're still tired. I'm expecting somebody cutting, somebody measuring, somebody getting isopropyl alcohol set up, somebody getting tape set up. Everybody should not be sitting. You guys should all be in there, or you won't finish an hour. Divide it up for people. Yeah.